So we're going to plug that ansatz in. So what we're going to get, first off right away, is the following. G of m plus 1, because I'm evaluating it, u of un at m plus 1, so that I get an m plus 1 here, times e to the I sigma n h. So left-hand side of the equation is equal to g of n, e to the I, h, plus lambda over 2. And what you get in here is g to the n, e to the I, c of n plus 1 h, minus g of n, e to the I, c of n minus 1 h. And there you go. There's your scheme. Oh, these are m's. Sorry. G of m. Okay? All right, notice there's a g of m, g of m, g of m, g of m plus 1, so I can divide through by g of m. And I just get a g on this side. Okay? So let's do this out. Okay. And I can also multiply through by e to the minus I sigma c of n h. Right? It's going to cancel that. It's going to cancel that. Sweet. So you get g is equal to 1 plus lambda over 2. Now you're going to get some stuff in here. You're going to get e to the I c of n plus 1 minus c of n h. Okay? Minus e to the I c of n minus 1 minus c of n h. Okay? So far, so good? Now, what we're going to assume is that the c of n are Fourier modes. So we're going to write them as n zeta, some new variable. These are basically going to see like cosine 0x, cosine 1x, cosine 2x. In other words, the harmonics of your domain of some sort. So you assume that the Fourier coefficients are just integers. Okay? What does that mean for here? Well, I have c of n plus 1 minus c of n. So this is going to be something like n plus 1 zeta minus n zeta. And look at that, I have n zeta minus n zeta, and I just get a, oh, sorry, those are zetas, not x's. Hard to tell the difference. It's just all about how the magic works in the wrist on the way down. Okay? Zeta, zeta. So two of them cancel out, and you're left with zeta h. Okay? Ready? You sure? Ready? Okay. So that means this becomes zeta h, and that becomes, this is minus 1 over here, so it's a n minus 1, so you get left with minus zeta h. And all of a sudden you have flashbacks. You recognize that? Excellent. So I can bring a 2, I can bring this 2 into there, right? And that means it gets rid of it there. And I can multiply by 1, which is I over I. Everybody agree with that? Oh, and it is sine. Sweet. Okay, so it's sine in disguise, but now we can just basically say, okay, G is equal to 1 plus I lambda sine zeta h. Pretty little result. Now what happens? What do we care about? We care about the absolute value of what this G is. And the absolute value of this G is simply equal to 1 plus lambda squared sine squared zeta h square root. Okay. Now you make your assessment. Is this scheme stable or not? There sits lambda. That's what we have control over. Is this thing bigger than 1 or 1 or less? I have 1 plus a positive number. That means this is always bigger than 1, right? Which means you're screwed, okay, if you're going to use this scheme. As advertised, this thing is unstable, no matter how you pick lambda. Okay? It's unstable because your G is bigger than 1. Done. Do not use this scheme. Now, when you had a primitive computer, these are things you should know ahead of time. Now the way computing goes is you go, I'll just program and see what happens. And I'll just make adjustments after the fact. Because it's cheap. You got these laptops, they just like, you could just crank away on stuff. You hit return, it gives you back your stuff. And instead of even thinking about ahead of time, you just wait till it crashes and go, oh, I must have done something wrong. I'll fix it up. This is how computing works today, right? Back then, you're like, okay, how much effort is going to take to make this computation? Right? He's working with a room full of people. And how pissed are they going to be when you say, oh, sorry about that. This is totally unstable. I know you've been doing it for the last week or so. It's been cool and all, but let's do it again. A different scheme. Okay? All right. Don't do the scheme. It's always unstable. And you can see how it worked. There it is. You plug stuff in. And it's limited, granted. It's a Fourier mode expansion, but it tells you that things are going to blow up. All right. Let's look at this equation again now, but now from the perspective. And since I'm going to cover a lot of schemes today, I'm going to do some board magic for you, which you'll not like probably. But that's okay. It's all in the notes. So it's okay. It's not like I didn't give you my notes so that you have to like keep up with writing. I'm just going to change the scheme around, and I'm going to consider, instead of the forward Euler scheme, so that's what this was. Remember, we also talked about the backward Euler scheme.